it is on Wednesday 1 to 2.
Okay, sir. Thank you, sir.
So it is fine with everyone, this tutorial time. Okay.
Yes, sir.
So is my slides visible to everyone?
Yes, sir.
Okay, so in the last class, what we have
Yes,
started.
sir.
Thank you. In the last class, what we have started looking at is we have discussed about the conduction first, and then we said that let's look at the steady state conduction through the plain wall. That is what we have seen, isn't it? But then in that case, we have not used any shell balance because we said that the cross sectional area is same, so we don't require a shell balance in such cases. Then we have further complicated our analysis and we have looked at the geometries where the heat transfer area itself is varying, isn't it? So the cases like cylindrical surfaces or the spherical surfaces, in such cases the heat transfer area also changes as we move along the conduction direction in a radial direction. Okay, so in such cases we require a shell balance. Then we have further complicated our analysis when we said initially we have looked at only the input and output, no generation, no accumulation, isn't it? But then again we have added one more complication saying that let's say if there is a generation of the heat inside uh, the conducting material, in that case even if you are looking at the slab, flat slab, there also we require a shell balance, isn't it? Unlike the previous case where we have not used a shell balance at all, when we have not used the generation term. But when we use the generation term, in such cases we also require a shell balance even if we are looking at the flat slab. Okay, so that is what we have seen in the last class, and towards the end we said that we will again extend this analysis to the cases where the heat transfer area is also changing along with the generation term. Is it all right? Hello, is there any questions so far, whatever we have discussed?
No, sir.
Okay, so let's start with this new case. In this particular example, what is been given is there is an electrical wire carrying current. So there is a metal wire, electrical metal wire through which the current is flowing. The radius of the wire is Ri, and since the electrical wire cannot be bare, so around that we in general have the electrical insulation. So the thickness of the insulation or the radius of this insulation layer is R0. Okay. The temperature of the outer surface of the insulation is T0. So this is a surface temperature. This T0 is a surface temperature. It's not an ambient temperature. We will look at this case also when we look at the convection. But right now, just a minute. Okay, sorry. So in this case, what we are saying that this temperature T0 is the surface temperature here outside. It's not the temperature of the ambient. Okay, even that case we will look at when we will look at the convection. But right now, let's assume that this T0 is the outer surface temperature here. The thermal conductivity of the metal wire is Km, whereas the thermal conductivity of the insulation layer is Kc. Again, volumetric rate of heat generation of the wire is psi v. We are assuming that the volumetric rate of heat generation is constant. Okay. And it is uniform throughout the medium. It's not a function of radius. That's what we are assuming. So psi v is a constant term which remains uniform throughout the medium. Okay. So now, as I said that there is a generation term. Also, the heat transfer is taking place in a radial direction, and therefore we have to make a shell balance in this case, because there is a generation term as at the same time there is a variation in the heat transfer area as we are moving along the radial direction. Is it clear to everyone?
Yes, sir.
Yes, sir.
So we are assuming a shell of thickness delta r at a radius r from the center. Okay, and again the length of the wire is L, capital L. Now in this particular case, the rate of heat input to the shell at the radial position will be area into heat flux at R, isn't it? So that is given as 2 pi RL into QR, small QR, where small QR is nothing but the heat flux along the radial direction, and this entire thing we are calculating at the radius R. So this area into small QR is nothing but what? Capital Q. Remember, in this case we are saying that we are basically calculating what is the capital Q input and what is the capital Q output, and also there will be a generation term. Okay, so the output in this case from the shell is rate of heat output from the shell at a radial position at R plus delta R is going to be again area 2 pi RL into the heat flux QR at a radial position R plus delta R. And what is the generation term? Generation term is going to be volume into psi V. So now volume of the shell is going to be what? 2 pi RL, that is the circumference, multiplied by delta R, that is the circumferential area into delta R, that will give you the volume of the shell. So 2 pi R delta RL is going to be the volume of the shell multiplied by psi V will give you the rate of heat generation in the shell. Okay. Now in this case there is no accumulation. What we are having is input plus generation equals to output. So input term is 2 pi RL small QR at R plus 2 pi R delta RL psi V, that is the generation term, and that the summation of these two should be equals to the output, and output is 2 pi RL QR at R plus delta R. Now this output term I can take it on the left hand side. What I will get is minus 2 pi RL QR R plus delta R minus plus 2 pi RL QR at R, and that is going to give me this term. If I remember, in this case this 2 pi, this term is going to be constant, so this 2 pi I can get rid of, 2 pi L I can get rid of directly, isn't it? That's the common term. So if I get rid of this 2 pi L term, then what I'm left with is RQR at R plus delta R minus RQR at R divided by delta R plus R psi V equals to 0, and this minus sign will be here outside. And now in this case, since delta R is a thickness of the radial shell and this thickness will be tends to 0, so definitely this first term in this equation is going to be what? Minus d by dr RQR plus R psi V equals to 0. So everybody is able to follow this, what we are doing? Hello?
Yes, sir.
Yes, sir. Sir, I think this is same as the transport phenomena course in that also is.
Yes, Achintya, yes. This is absolutely the same as what you have looked at in a transport phenomena. Okay, all right. So in this case, we are getting this equation minus d by dr RQR plus R psi V equals to 0. Here this QR is nothing but the heat flux at the radius R, isn't it? And that can be obtained using the Fourier's law of heat conduction as minus Km dTm by dr, isn't it? Again, we are, for a simplicity, we are assuming that this the thermal conductivity of this metal wire is constant. It is not varying with temperature. So we are writing this as minus Km dTm by dr, and that is what we are putting it here. So this Km, since it is not a function of temperature, the constant term, I can take it out here. So what we get is d by dr R dTm by dr plus R by Km psi V equals to 0. So are you all able to follow what we have done so far till equation number 3? Till equation number 3, is it clear to everyone what we are doing?
Yes, sir.
Now So far we have done the shell balance only in this metal wire. This is the metal wire. Remember, up to Ri there is a metal, isn't it? From 0 to Ri, it's a metal, and from Ri to R0, it's a insulation. Correct. Now this is what the final equation which we have obtained. This equation we can integrate. This equation we can integrate and find out the distribution of the temperature, but the integration will require two constants, and that two constants can be obtained only by looking at the boundary conditions. So what are the boundary conditions in this case? Unlike the previous case where we have looked at the flow of steam or flow of hot fluid through a pipe, the inside temperature was given. The inside temperature was given at R equals to Ri, T equals to Ti. That is what we have used in the earlier example, if you remember here. Remember, in this case, this is the earlier example which we have seen, isn't it? So in this case, what we have used is at R equals to Ri, the temperature is Ti, and R equals to R0, temperature is T0. That is what we have used. But unlike this case, in the present situation, you can see it's not a hollow pipe. It's not a hollow pipe. It's a metal wire. It's a metal wire, isn't it? Correct. And which is starting from R equals to 0 to Ri. Correct. So now in this case, the boundary condition is at R equals to 0 at the center. What we are assuming is the temperature is going to be finite. And the typical boundary condition used in such cases is dTm by dr equals to 0. Isn't it? So change in the temperature with respect to R at the center is going to be 0. That is what we are assuming. This is the boundary condition we use in all such cases. Correct? Do you all agree? This you might have seen in your transport phenomena as well.
Yes, sir.
Okay. So this is the first boundary condition. First boundary condition is at the center we are assuming that the temperature is going to be finite, and what it means is dTm by dr is going to be 0. Now second boundary condition, unlike the previous case where the second boundary condition was at R equals to R0, T will be T0. But in this case we cannot apply that because outside temperature T0 is with respect to the insulation. It is not with respect to the metal wire. Remember, our metal wire is only up to Ri, and we are interested in finding out the boundary condition at Ri because we are solving this equation only for a metal wire so far. But this temperature which is there at the interface of this insulation and the metal wire, this temperature is not known. This is not known, isn't it? It's unknown. So how to solve this situation? Did you see the problem here?
Yes, sir.
Isn't it? So see, initial boundary condition we have used that the dTm by dr equals to 0. That's simple. But second boundary condition at R equals to Ri we will not be able to apply because what is the temperature at this interface of insulation and the metal wire we don't know, isn't it? Correct? Because if we increase the thickness of this insulation, maybe the temperature at this insulation and the metal boundary is going to be lower. So it depends on how much insulation you are putting, what is the thickness of the insulation, what is the thermal conductivity of the insulation. All these factors are going to play a major role on what will be the interface temperature here. Isn't it? So how to solve this problem then?
Sir, at R is equal to Ri, we can apply a condition that all the heat which is going from the metal wire will be traveling to the insulation itself.
Yes, yes.
And then we can write an equation for the heat transmitted within the insulation, and then we can apply the boundary condition at R is equal to R0, that temperature becomes T0.
Precisely, precisely. Perfect. But another complication here is, see, the metal wire is generating, there is a generation of heat taking place in the metal wire, but there is no generation of heat taking place in a insulation. Okay, so that is also we have to keep in mind, but whatever you have said is absolutely correct. We have to look at the heat balance between this insulation and the metal wire at this interface, and then we have to identify the temperature. So in addition to the shell balance which we have done at this metal wire, we also need to do a shell balance in this insulation layer. Do you all agree?
Yes, sir.
Yes, sir.
Okay. We also need to do a shell balance in this insulation, but in that case, we will not have a generation term. Remember the shell balance which we have used here, we have used a generation term, but that generation term is not going to be there in the insulation because insulation is not going to generate the heat. All right.
Sir, I have a doubt here.
Please go.
Sir, you said that we have to do heat balance on the insulation and we have to do heat balance on the inner side of the cylinder, means a pipe.
There's no inner side of the pipe, Achinta. This is the metal wire is there inside and outside there is a insulation. What I'm saying is the metal wire which is there inside is carrying a current, and since there will be some resistance to the flow of the current, heat will be generated in the metal wire. So that is why we are using a generation term in this shell balance of this metal wire. Whereas the insulation which is outside and no current is flowing through this insulation layer, and therefore heat will not be generated in the insulation layer. Again, in order to solve the equation, we require this interface temperature between the insulation layer and the metal wire, and this interface temperature is unknown because this temperature will depend on not only the heat balance of the metal wire but also the heat balance of the insulation. Both. That's why both these layers we have to look at together.
Sir, the temperature at RI means that we have to find the temperature at RI.
Yes.
And sir, so you said that we have to balance means the flux at the heat flux at RI with the Q. The heat flux at the interface would be the same. The means the heat flux coming from the metal pipe and the heat flux going into the insulation at the interface would be the same.
I am not saying that heat flux will not be same. I am saying, remember, whenever there is a change in the area, heat transfer area, heat flux is not same. What is same is capital Q. Capital Q, provided that there is no generation term. But at this interface, we can still equate that the capital Q from this metal wire will be same as Q passing through this insulation because there is no generation term in the insulation. So at the interface.
Yes, sir.
Okay, all right. So is it clear to everyone what we are saying and what we are discussing? Hello?
Yes, sir.
Please stop me if something is not clear. We will discuss it 10 times. Okay, no issues in that. Please stop me if something is not clear. Please bother me in between if something is not clear. It's perfectly all right. Okay. Let's move. Yes, is there any question? Sorry.
So here the for both the material the area is the same, then why can't we?
It's not area. Who said area is same? As we are moving along the radial direction, my surface area is going to vary. This is the cylinder. Remember, this is the cylinder. It's not the slab. It's a cylinder. If you are moving in a radial direction, depending on at what radius you are, your surface area is going to be different. Cross-sectional area is going to be different, isn't it?
At the interface for both at RI for both the metal wire and the insulation area would be same at RI.
Okay.
Then why can't we equate the flux because heat flow is just.
Yes. You are absolutely true. At this interface, we can apply that. Yes.
Yes, sir. I was saying that only that at the interface the flux would be same.
At the interface that will be same. Yes, at the interface because area is going to be same, so that is going to get cancelled out. Yes. So small QR at this interface from this metal and from this insulation, both are going to be same. Yes, absolutely true. Yes. Okay. All right.
And sir, one more point I want to clarify. That you said that rate would be same, means Q1 A1 is equal to Q2 A2. We can apply this, means heat
doesn't
flux.
matter because A is going to cancel out. Yes.
Yes, sir.
Capital Q also can be equated. Small q also can be equated at this interface. There is no problem at this interface. Only at the interface. All right. Okay, so as I said that to solve this problem, we need to make a shell balance not only in the metal wire, but also in a insulation. Now this equation number 3 is a shell balance for a metal wire, and the boundary conditions we have assumed here is dTm by dr equals to 0 at r equals to 0, and at the boundary of the insulation the radius will be Ri. So the temperature there is going to be Tc, but this Tc is unknown so far. Okay, this Tc, which is nothing but the temperature at the boundary of the metal wire and the insulation, this temperature Tc is unknown. So even though we are applying this boundary condition, but this will be unknown. Okay. So since this Tc is unknown, we need to make a shell balance for the insulation. And again, if we apply the shell balance to the insulation, we are going to get the same equation as that of equation number 3, except it will not have a generation term. Remember, there will not be any generation of heat in the insulation. So therefore, this second term which is there in the equation 3 will not be there if we apply the shell balance for the insulation. And what we are going to get is d by dr R dTc by dr equals to 0, where Tc is nothing but the temperature distribution across the insulation layer. Do you all agree? Do you all agree with this equation number 4?
Yes, sir.
So we have just omitted this generation term because there is no generation term in the insulation. Yes, some question was there in between.
Sir, can you please explain the boundary condition at r equals to 0?
See, r equals to 0, what we are assuming that dTm by dr. So what we are doing here? Here we are assuming that this temperature Tm is finite. So we are assuming that the temperature Tm is not changing at the center. Remember, up to this, okay. Up to this, if you move along the radial direction from r equals to 0 and r below, you can see that the temperature is changing. But at the center, temperature is not changing. That's what we are assuming. Okay. Is it clear?
Sir. Yes.
So why are we assuming this? How can we assume?
So it's not. It's not assumption. It's what you are going to see. We are saying that it's not. I'm sorry for using that word assuming. It is going to be like that only. Okay. So temperature here at the center is going to be. It's not going to vary. It's going to be same because see, if you move along this direction also it is going to vary. If you are moving up, it is going to vary. But at the center, it's going to be the same. It's not changing with radius at r equals to 0. All right.
Okay.
Okay. So now this second equation we have obtained as d by dr r dTc by dr. This is going to be the balance equation for how the temperature is going to be distributed across the insulation layer, and we have omitted this generation term because there is no generation occurring in a insulation. Now in this case, what will be the boundary conditions? The boundary conditions here, outer boundary condition is clear. At r equals to r0, Tc will be T0. That is what is been given here also, isn't it? At r equals to r0, the outer temperature is T0, isn't it? And at r equals to ri, my temperature Tc is going to be just Tc. That is what we have used. This Tc is nothing but the boundary, the temperature at the insulation and the metal boundary. I could have used some other notation here because now this Tc is getting confused with this Tc. But remember that this Tc here is a boundary temperature and this Tc is the temperature distribution. Okay. Is it clear to everyone?
Yes, sir.
Okay. So now again in this case, okay. So now let's try to solve the entire problem formulation with respect to these two equation and these 4 boundary conditions. Okay, so let's start with this original equation 3. Original equation 3, if we integrate, what we get is r dTm by dr equals to r square minus r square divided by 2 km psi v plus C1. This is what you are going to get if you integrate this equation number 3, isn't it? Then you can apply the first boundary condition. This first boundary condition is this dTm by dr equals to 0, isn't it? If you apply this, what we get is this dTm by dr becomes 0 and r is already 0. So that means you get C1 equals to 0, isn't it? So this C1 we have already obtained. So with C1 equals to 0, the equation left with is this, isn't it? R dTm by dr equals to minus r square divided by 2 km psi v. That's it. Okay, we can rearrange this equation, and after rearranging, what we get is this r will be divided here. So we will get dTm by dr will be given as r divided by 2 km psi v, and we can further integrate this equation number 6. And after integration, what we get is this Tm will be obtained as r square 4 km psi v plus C2. Now this C2 is unknown. Is it clear to everyone what we have done so far?
Yes, sir.
So we have integrated.
Sir, how we calculated C1? Can you show how we calculated constant of C1?
So this is the equation which we have obtained after first integration, isn't it? Now apply the first boundary condition. What is first boundary condition?
Okay. R is equal to 0. Okay. dTm by dr is equal to 0.
So this dTm by dr becomes 0 and this r is also 0. So this second term here on the right hand side is also 0. So you get C1 equals to 0, isn't it? So what we left with is this r dTm by dr is equals to minus r square by 2 km psi v. Now this equation we can further integrate with respect to r. And what we get is Tm equals to minus r square 4 km psi v plus C2. Clear? Is it clear to everyone now?
Yes, sir.
Now this C2, as we have discussed extensively, that this C2 we will not be able to get it easily, even though second boundary condition is at r equals to ri, Tm equals to Tc. But this Tc itself is unknown, isn't it? So that's why let's keep it this equation as it is. And let's look at the temperature distribution in a insulation layer now. So this is the equation which we have obtained for the temperature distribution in the insulation layer, isn't it? D by dr into r dTc by dr equals to 0. That is what we have obtained here, isn't it? See, correct? This is the same term without the generation term, isn't it? Yes or no? Hello?
Yes, sir.
Yes, sir.
So again, we can integrate this equation twice. What we get is Tc equals to C3 ln r plus C4. Now, in this equation also we can apply two boundary condition, but second boundary condition we can apply easily because that is the outer temperature, isn't it? Outer temperature is already given. So this Tc becomes T0 when r equals to R0. So we get T0 equals to C3 ln R0 plus C4. This is the second equation, and the first equation, if we apply the initial condition, which is at r equals to ri, Tc equals to just Tc. So that becomes Tc equals to C3 ln ri plus C4. Correct. Here this Tc is nothing but the interface temperature. That's why I'm saying I should have used a different notation here. Okay, all right. But can you all able to see what I'm trying to say here? This is the interface temperature between the metal boundary and the insulation. So when you are going to get that, when r equals to ri. So that's what you are putting here. R equals to ri, temperature Tc just equals to Tc. So Tc equals to C3 ln ri plus C4, and the second equation is T0 equals to C3 ln R0 plus C4. I can subtract both these equations. So after subtracting the C4 get cancelled out. So what we get is Tc minus T0 is C3 ln ri by R0. Isn't it? If I rearrange this, Tc equals to T0 plus C3 ln ri by R0, where this Tc is the interface temperature. This interface temperature. Now this interface temperature here, this is unknown. This is unknown, and also this C2 is unknown here. Okay, correct. This C2 is unknown, and if we apply the
C3 is also unknown because T0 plus C3 don't know what is C3.
We will calculate that. Yes, you are absolutely true. This C3 is unknown, C2 is unknown, isn't it? These are the two things which are unknown so far. Okay, so now this Tc, let's apply the second boundary condition in this TM equation. So second boundary condition is what? At R equals to Ri, this TM becomes TC, isn't it? So we get TC equals to Ri square by 4 Km psi V plus C2. Now this is in terms of TC. This equation is also in terms of TC, so we can equate both these equations, isn't it? So what we get is T naught C3 ln Ri by R naught, and that is equals to the same minus Ri square by 4 Km psi V plus C2. Now in this entire equation, there are two unknowns, C3 and C2. Do you all agree?
Yes.
Is it clear what we are doing?
Yes, sir.
So remember what we are doing is this temperature distribution across the metal wire we have calculated as TM. Similarly, the temperature distribution across the insulation we have calculated as TC. Both TM and TC has a common boundary condition, which is at R equals to Ri, the temperature is going to be TC. So both these common boundary condition we have applied in both these equations, and then we have equated these two, isn't it? So because if we apply the boundary condition, both these temperatures are going to become TC, and then we can equate these two right hand side. That is what we have done here, isn't it? So T naught C3 ln Ri by R naught equals to minus Ri square by 4 Km psi V plus C2. Now in this equation, there are two unknowns C3 and C2. This we have to calculate. Is it clear to everyone? Hello?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So how we can calculate this? We can calculate this by applying the continuity equation. As our friend initially said that at interface we have to equate the flux, isn't it? So that's what we are doing at the interface. We are equating the flux. So what will be the flux coming out from the metal wire? The flux coming out from the metal wire will be minus Km dTm by dr. That is what is going to be QR at R from the metal wire, isn't it? And that should be the same as the flux received at the insulation, isn't it? So that is given as minus Kc dTc by dr. Both are going to be same. So we can equate these two, isn't it? Now dTm by dr we already know. So this is the Tm, we can differentiate this. So dTm by dr we are going to get, we got it directly here. dTm by dr is going to be R by 2 Km psi V, isn't it? And if we multiply that by Km, what we get is minus Ri by 2 Km. If you multiply by Km, what we get is minus Ri by 2 psi V. Isn't it? That's what we are going to get as a dTm by dr. Correct. Similarly, we can calculate dTc by dr also. This is the TC at the interface. C3 ln R plus C4. Isn't this the TC at the interface? We can differentiate this. dTc by dr is given as C3 by Ri, isn't it? At the interface. And this we can equate. So Kc dTc by dr will be Kc C3 by Ri, isn't it? And that is same as minus Ri by 2 psi V. So from this we can find out C3 directly. So C3 comes out to be Ri square by 2 Kc psi V.
Sir, can you explain from here one more time? dTm by dr is equal to minus Ri by 2 Km psi V.
So R dTm by dr is given by this minus R square by 2 Km psi V, isn't it?
Sir, 1 minute. How this means? I forgot how this came. Means
We have solved this equation here, isn't it? This is the equation which we have obtained initially. We have integrated this equation with respect to R. We have obtained R dTm by dr is given as minus R square by 2 Km into psi V plus C1. But this C1 is 0. So what we get is R dTm by dr is given as minus R square by 2 Km psi V. This R I can take it on the right hand side. What we get is dTm by dr as R by 2 Km psi V. Correct? Achintya?
yes, sir.
So is it clear to everyone how we have got these terms? So dTm by dr we have obtained here, dTm by dr, and we have multiplied by Km. So what we get is minus Ri by 2 psi V. So dTm by dr K dTm by dr at Ri we are calculating, and that should be equals to K Kc dTc by dr at R equals to Ri. So we have calculated K dTm by dr at R equals to Ri, and that comes out to be minus Ri by 2 psi v. Similarly, we have calculated Kc minus Kc dTc by dr from this equation, which comes out to be Kc C3 by Ri, and both these we have equated. And after equating, in this case, the only unknown is C3, so we have obtained directly C3. C3 comes out to be minus minus Ri square by 2 Kc psi v. Is it clear to everyone?
Yes, sir.
Now this C3 we can put it in this equation number 8. We can put it in the equation number 8 and we can calculate C2. So we have obtained C2 also. So all unknowns we have calculated now based on this. Is it clear? Yes or no?
Yes.
So we, after putting this C3 in this equation number 8, we can calculate. Remember, in this equation number 8, there are two unknowns, C3 and C2. If we put C3 directly here, then we can calculate C2. So C2 comes out to be this T naught plus Ri square psi v by 4 in the bracket 1 by Km minus 2 by Kc ln Ri by R naught. Now this C2 and C3 we know. We can put this C3 and C2 in the original temperature distribution equation. So this is the temperature distribution equation for metal wire. We can put this C2 here and we can find out how the temperature distribution across the metal wire is going to be. Similarly, we can put C3. We can put this. Remember, from this we can calculate. Tc minus T naught. From this equation we can calculate C3, isn't it? So this is the temperature distribution across the insulation. In this case we have unknown C3 and C4. Correct. Now by applying the second boundary condition, we get T naught equals to C3 ln R naught plus C4, isn't it? So this C3 we can put it here. The C3 which we have calculated already now. That C3 we can put it here and we can calculate C4, and then C3 and C4 we can back substitute in this original equation and we can calculate how the temperature distribution across the insulation is going to be. That is going to be obtained from this equation. Is it clear to everyone? Yes or no?
Sir, just can you move to the previous slide? I just want to see the previous steps.
Here?
No, no, sir. Before this. Yeah, before this.
This is the previous slide.
The first slide. Yes, sir. This.
Hello? Is it clear to everyone what we are doing so far? So once we have obtained, okay. So once we have obtained C3 and C2 here, this C3 and C2 we can back substitute in the original distribution equation in equation 6 and this equation here, and we can calculate the temperature distribution across the metal wire as well as the temperature distribution across the insulation. That's what we have done in the subsequent slide. We have put the C2 in 6. We have calculated the temperature distribution across the metal wire, which is obtained by this equation. It looks complicated, but if you put it carefully, you will get this equation. Similarly, we have calculated the interface temperature. This is the interface temperature. This is not the distribution. This Tc is just the interface temperature. Remember, this Tc is directly coming from this equation. This equation, isn't it? Tc equals to minus R square 4 km psi v plus C2. Remember, here this Tc is nothing but the interface temperature. So this Tc is nothing but the interface temperature. Maybe I'll just write it so that no confusion is there. Interface temperature. This is the interface temperature. For distribution, for temperature distribution, you need to put these constants which we have obtained. Just a minute. Is my slides visible to everyone?
No, sir.
Okay, all right. Just a minute.
When you're using TC, is it having two different meanings in the whole derivation?
Just a minute. Let me share the file again. Is it visible now? So this TC is a interface temperature. That is what is written here also. They see temperature exactly at the boundary of metal and insulation. This is what we are going to get. But for temperature distribution in the insulation, put C3, C4 in equation number 7. Put C3, C4 in this equation. C3, C4 in this equation you can put and you can find out the temperature distribution. Is it clear to everyone?
Sir, in the equation TC is equal to C3 ln R plus C4, we have to put the C4 in this the line from the line which is yes, the arrow which is
Yes,
yes,
we have to put. Here we have to put. Yes.
So this is not showing the interface temperature, but this is showing the temperature profile.
Distribution, correct.
Temperature profile.
Yes. You are absolutely correct, Achintya. Maybe I just rename this as A. Maybe I rename this as A.
And sir, if it has been the interface temperature, then it would have been ln Ri, because interface temperature is at Ri. But if we are storing the temperature profile, then it would be R only.
Just a minute, Achintya. Is my slides visible to everyone? Hello?
Yes.
Yes, sir.
Okay.
Yes, sir.
So I have just wrote it here also. So for temperature distribution in insulation, put C3 and C4 in equation number A. Equation A. So equation A is this equation. Okay. In this equation, you have to put C3 and C4. C3 you have already calculated. C4 you can calculate it from both these equations. So C4 you can calculate here and put that C4 in this, and C3 you already know. So that's how you can calculate TC. Okay, but what TC is calculated right now, this is a interface temperature. This is not a temperature distribution. Don't get confused. That's why I have clearly written interface temperature exactly at the boundary of the metal insulation. But this TM we have calculated. This is the temperature distribution across the metal wire. Is it clear to everyone now? Hello? Hello?
Yes, sir. Yes, sir. Yes, sir.
Can we go ahead? Unless if there is any question. Hello?
Yes.
Can we go ahead?
Yes, sir.
Yes.
Okay. So let's solve another, similar problem for a spherical geometry with steady state conduction through a sphere with a heat source. Okay. So this particular schematic here is for a sphere. Again, we are assuming that at R equals to Ri, the temperature is Ti, and at R equals to R0, the temperature is T0. And since the area is also conduction area is varying as we are moving across the radial direction, and also there is a heat generation term, we need to make a shell balance. So consider a shell of thickness delta R at the radius R from the center. Now the rate of heat input to the shell at the radial position at R will be given as area, which is nothing but 4 pi r square for a sphere, into heat flux QR at R. Similarly, the rate of heat output from the shell at the radial position at R plus delta R is going to be 4 pi r square QR R plus delta R, and rate of heat generation in the shell is going to be volume into volumetric rate of heat generation. So volume in this case is going to be 4 pi r square into delta R. That is going to be the volume of this shell. So volume of this shell multiplied by the rate of volumetric rate of heat generation psi v, that gives me the total heat generation in the shell. Now, the shell balance in this case is going to be rate of heat input plus generation should be equals to the output. So heat input is this 4 pi r square QR at R plus generation term is going to be 4 pi r square delta R psi V, and that should be equals to output, which is nothing but 4 pi r square QR at R plus delta R. We can rearrange this equation. After rearranging this equation, what we get is this R square QR at R plus delta R minus R square QR at R divided by delta R plus R square psi V equals to 0. Now this first term in this equation will be written in terms of differential. So we can write this equation as d by dr R square QR, because this delta R is tends to 0. So we get minus d by dr R square QR plus R square psi V equals to 0. So is it clear? Everything is
Sir,
clear?
I wanted to ask, sir, why it is minus, like minus R square QR R plus delta R minus R square QR delta R? Why it is written outside minus? This minus.
Minus because see this right hand side, if you take it on the left hand side, what you are going to get? Minus. So see, remember here there is a bracket here. So this minus, if you multiply here, you get R minus R square QR, isn't it? And this minus here will get cancelled out. You will get plus R square QR. So you are having a plus R square QR term on the left hand side. You can see here. This R square QR term is a positive term here. Whereas if you take this right hand side on the left hand side, it will become negative. Is it clear? Yes or no? Hello?
Yes, sir. Yes, sir. Yes, sir. Yes.
That's why this minus sign I have taken it out. There is a bracket here. Okay. There is a bracket here. Is it clear to everyone what we are doing? Hello? So this equation is same. This equation is same as the equation which we have obtained earlier for this case, isn't it? This the equation is same, except there is a plus. There is a plus R square psi V term is there here in this equation, because when we have looked at only the steady state conduction through sphere, no heat generation source we have assumed. So in that case, we have obtained only d by dr R square QR equals to 0. But when we are assuming the heat generation source, then we additionally have this R square psi V term here added. Is it clear to everyone? Hello? Yes or no?
Yes, sir.
Yes, sir.
Now we can rearrange this equation. We can by putting this Fourier's law of heat conduction. So Fourier's law of heat conduction in this case is going to be QR is given as minus K dt by dr, isn't it? So if you put this QR equals to minus K dt by dr in this equation, what we get is this minus sign get cancel out. What we get is d by dr is R square K dt by dr plus R square psi V equals to 0, isn't it? Again, we are assuming that this K is independent of temperature, isn't it? So we can take it out, this K we can take it out from this equation, and after rearranging, what we get is d by dr R square dt by dr is given as minus R square psi V by K, isn't it? And we can integrate this equation with respect to R. So after integrating this equation with respect to R, what we get is R square dt by dr is equals to minus R cube psi V by 3K plus C1. Okay. Now, okay. So I think, all right. This figure I need to modify, because here the problem which we are solving is we are not assuming a hollow sphere here, but we are assuming a solid sphere. Remember, we are assuming a solid sphere. So then this Ri will not be there. This boundary condition will be. That is why this boundary condition is that R equals to 0, dt by dr equals to 0. Okay, so I will just change this figure. Just a minute. Just a minute, I will immediately change it. This is not required. This is it visible to everyone what I'm doing?
Yes, sir.
Yes, sir.
This RI term will not be there, and this will be a okay. All right. So this is the solid sphere. So here at R equals to 0, at R equals to 0, our boundary condition is going to be dt by dr equals to 0. Is it clear to everyone? This is the same boundary condition which we have used earlier, isn't it? And at R equals to R naught, the temperature T is equals to T naught. We can apply both these boundary conditions here. So if we apply this first boundary condition in this equation, we directly get C1 equals to 0. Isn't it? So C1 we directly get it 0. So then we can again integrate this equation with respect to R. And what we get is dt by dr is R psi v by 3k. Sorry, dt by dr will be given as minus R psi v by 3k. And if we integrate further, what we get is T is given as minus R square psi v by 6k plus C2. Is it clear to everyone? Yes or no?
Yes, sir.
Yes, sir. Yes.
Now in this case, the only unknown is C2. C2 we can directly obtain by applying the second boundary condition. At R equals to R naught, T equals to T naught. So we get T naught is minus R naught square psi v by 6k plus C2. And from this C2 is obtained as T naught plus R square, R naught square plus R naught square into psi v by 6k. And if we put C1, C2, both these in this original equation, we get the temperature distribution as T naught plus psi v by 6k R naught square minus R square. So this is the temperature at any radius R. Do you all agree? Do you all agree?
Yes, sir.
Now from this equation again we can obtain what will be the maximum temperature. So maximum temperature can be directly obtained. See, in this case the temperature is varying across the radius, and where the maximum temperature we can get. If we look at this equation, T naught is a finite number. The maximum temperature you can get it only at
the center,
0, isn't it? So this R, when you put this R equals to 0, then only you will get this T as maximum temperature that you can directly obtain here. So T max comes out to be T naught plus psi v R naught square by 6k. Is it clear to everyone? Hello?
Yes, sir.
Yes, sir.
Okay. Okay, so let's look at one example solved based on whatever we have seen today. So in this example, a current of 200 ampere is passed through a stainless steel wire with a thermal conductivity of 19 watt per meter per degree Celsius, and the diameter of the wire is 3 mm. The resistivity of the steel may be taken as 17 micro ohm centimeter, and the length of the wire is 1 meter. The wire is submerged in a liquid at 110 degrees Celsius and experiences a convection heat transfer coefficient of 4 kilowatt per meter square degree Celsius. Calculate the center temperature of the wire. Now what is been given here is there is a wire through which 200 ampere current is passing, and because of that this wire will get heated, isn't it? Now this wire is submerged in a liquid submerged in a liquid of temperature, let's say 110. But this 110 degrees Celsius temperature is the liquid temperature. It's not the temperature of the surface of the wire. No, both are different. Okay. So there will be a convective heat transfer taking place between the wire and the liquid. And that convective heat transfer coefficient is given as 4 kilowatt per meter square degree Celsius. We have to calculate the center temperature of the wire. So there are two things what we have to look at. First, we have to calculate the surface temperature at the wire surface. And from that, then we have to calculate the center temperature. Is it clear? Is it clear?
Sir, 110 degrees Celsius is the ambient temperature.
You
Ambient
can
temperature.
say it's not a it's a ambient temperature, ambient liquid temperature, isn't it? So liquid is present around the wire, isn't it? So that liquid temperature is 110. But the temperature of the wire is not 110. The surface temperature of the wire will be different. First, you have to calculate the surface temperature of the wire, isn't it? And then based on that, you have to calculate what will be the center temperature. Now, in this case, see, the heat is only generated by the wire. There is no heat input to the liquid from any other source, isn't it? So whatever the convective heat transfer taken between the liquid and the wire, it will be the same as the heat generated by the wire, isn't it? Whatever the heat taken out by the liquid from the wire will be same as the amount of heat generated by the wire. And amount of heat generated by the wire is given by what? Whatever the electrical energy dissipated in terms of heat, that will be the heat generated. So heat dissipated can be calculated as I square R, isn't it? Where I is the current flowing through the wire and R is the resistance. Now in this case, the resistivity is given, but resistance is not given. So this resistivity we can convert to a resistance using this particular formula. So rho is given as 17 micro ohm centimeter. We can multiply that by a length of the wire and divide by the area, cross-sectional area of the wire. Then we get the resistance. So resistance is calculated as rho into L by AC, where AC is the cross-sectional area. Rho is given as 70 into 10 raised to power minus 6 because it is given in micro ohm, isn't it? Into L. L is 3 mm in diameter is given. So, sorry, diameter is given 3 mm, length is 1 meter, isn't it? But again, okay, just a minute. Some unit problem is there. (17 micrometers), so 10 raised to minus 6 is added, but it is in a centimeter. So the length has to be multiplied in again centimeter. So 1 meter, so that is 1 meter will be again given in a centimeter. So that is 100. That is will be centimeter square, and this pi r square, this has to be again in a centimeter square. So is it correct? These units are correct? Just check. Hello? So 3 mm is there.
Yes, sir. The diameter is converted into centimeter.
Centimeter. That's why. Okay. So this is again a centimeter square in the numerator, as well as this diameter is converted in a centimeter square. Area is calculated in terms of centimeter square. So that centimeter get cancelled out. Okay. All right. Okay. So this resistance comes out to be 0.099 ohm, and this we can put it in this equation. So I square R gives me the amount of heat dissipated by the wire, and that will be the amount of heat taken by the convection, isn't it? So heat taken by the convection is HA delta T. This is what the Newton's law of cooling is. We will see this later in more detail, but for a time being, you can assume that this is correct. So HA delta T is nothing but the amount of heat taken out by convection, where delta T is calculated as wall temperature of the wire minus the ambient temperature T infinity. So wall temperature is unknown here, and the ambient temperature T infinity is given as 110. H we already know 4 kilowatt, so that is 4 into 10 raised to power 3 watt per meter square per degree Celsius. And area we can calculate. Heat transfer area in this case will be the circumferential area of the wire, so that is nothing but pi dl. So pi dl is this diameter into L. So we can back calculate the wall temperature. So wall temperature comes out to be 250 degrees Celsius. Is it clear to everyone what we are doing?
Sir, circumferential area means pi dl, how it comes like.
So remember the heat is transferred from the wire. Transferred from the wire in a radial direction, isn't it? So that is what will be the circumferential area of the wire. It is pi dl. This area, this AC is nothing but the cross-sectional area of the wire. When we are calculating the resistance, there we are looking at the cross-sectional area of the wire. Cross-sectional area of the wire is going to be what? Circle. Correct. So that's why we have used pi d square here. But in this case, when the heat transfer, we are looking at the heat transfer from the wire. We are looking at the heat transfer from the outside of the wire to the liquid, isn't it? So in that case, we have to look at circumferential area. That is going to be pi dl.
Sir, so the circumferential area would be 2 pi r L, na? Circumferential area 2 pi r L. 2 pi r L. 2 pi r L.
So that is why we have used pi dl. D is the diameter here, isn't it?
Okay. Means I thought, okay. This is the diameter.
Okay, so from this we can back calculate the wall temperature. So wall temperature comes out to, this is the wall temperature of the wire, which comes out to be 315 degrees Celsius, correct? Now this wall temperature, okay. Now what is been asked in the problem? In the problem, we have to calculate the center temperature of the wire. Isn't it? Okay. Now, this is the same system which we have looked at earlier.
Back from a search.
This is the same system which we have looked at earlier. So this is the system which we have looked earlier, isn't it? There is a wire, electrical wire, through which the current is flowing, isn't it? And this bare wire is put into the water. So unlike the insulation which was there earlier here, unlike that, this the bare wire is put into the liquid. So the only difference is in the given system is this insulation is not there. Do you all agree with me?
Yes, sir.
Yes,
Okay.
sir.
So same equation we have to use in this case also. Same equations we have to use, but except the insulation term. Now, since the wire is carrying the current, there will be heat generation. So first we have to see in that analysis, we have looked at this volumetric heat of generation. So first we have to calculate the volumetric heat of generation. So volumetric heat of generation is what? The total amount of heat generated divided by the volume of the wire, isn't it? Correct. Because the only generation term is only the heat input in this particular problem is by generation. There is no heat input outside, isn't it? Only the heat coming in the system is from the generation. So the total heat which is there, this 3960 watt is the total heat generated. This total heat generated is primarily from the generation term. So that is given as volume into generation term. Isn't it? So volume into psi V is going to be 3960. So volume in this case, volume of the wire will be what? Pi r square L. We can back calculate the psi V. Psi V comes out to be 5.602 into 10 raised to power 8 watt per meter cube. Do you all agree? Hello? Do you all agree?
Yes, sir.
And why we have calculated psi V?
Yes, sir.
Why we have calculated psi V?
To find the core temperature of wire.
We have calculated psi V because all our model equations we have written in terms of psi V here. Here all our model equations we have written in terms of psi V. isn't it? So this psi v we wanted to calculate. Also, we have calculated the surface temperature. Surface temperature at Ri equals to Tm. What is the surface temperature Tc? This we have already calculated now. Tc is 100, 215, isn't it? That's what we have calculated, surface temperature. So surface temperature is known, psi v is known. I can calculate what is the value of Tm at the center. Yes or no? Yes or no?
Yes, sir. Yes, sir. Yes, sir.
Now again we will follow the same model equation. Now unlike this original case we have looked at where the insulation was there, in the problem there is no insulation. So this equation again we have to solve for a modified boundary condition. What will be the modified boundary condition? At r equals to 0, dTm by dr equals to 0, this first boundary condition is going to be there. But at the insulation, sorry, instead of insulation, at r equals to r naught, my Tm is going to be what? T naught. That is what
T naught.
T naught. And T naught in this case is going to be 215. That is what we have calculated from this equation. This is what we have calculated, isn't it? 215 degrees Celsius. That is what is going to be T naught. Correct. So once we know that, then again we have to calculate what will be the temperature distribution. Temperature distribution. So temperature distribution comes out to be this. Tm is psi v r square by 4k plus Tw. That is what you are going to get. Okay. So this Tw is nothing but this 215. That is what we are we can derive from this. Remember, this is what the equation we have obtained. From this, the first boundary condition, if we apply, we get this r dTm by dr equals to r square by 2 km psi v, isn't it? Then if we integrate further, we get Tm equals to minus r square by 4 km psi v plus C2. Here we can apply the second boundary condition, and the second boundary condition is what? Second boundary condition here is at r equals to r naught, Tm will be equals to Tw. If we apply that, what we are going to get? C2 will be obtained as Tw plus R naught square divided by 4 km into psi v. And if we back substitute in this original equation, we will get Tm will be equals to Tw plus R naught by 4 km psi v minus R square by 4 km psi v. And when we are calculating the maximum temperature, that R becomes 0, and therefore you are going to get Tm at the center will be given as T naught plus R naught square divided by 4 km psi v. Do you all agree with me or not?
Yes, sir. Yes, sir.
So this equation here, in this equation you have to apply the second boundary condition, and the second boundary condition is Tm is Tw at r equals to r naught, and that is going to give you C2. Then that C2 you have to back substitute in this equation 6. You will have both terms, r terms as well as r naught terms. All the r terms are going to get cancelled out at r equals to 0. At r equals to 0 you are going to get the maximum temperature Tm, isn't it? Is it clear or not clear? Yes or no?
Yes, sir.
Or do you want me to derive again?
Sir, so in this, ultimately we have find the temperature profile, and to find the maximum temperature, we have put R is equal to 0.
Yes. So see, okay, I will do it. Just a minute. Okay. Let me open the whiteboard. I think then I will probably able to. Let me open the whiteboard. Then we will derive it again. Just a minute. going to take 1 or 2 minutes. Give me a minute. I think it takes time. So is it visible? So my whiteboard is taking some time. Is it visible to you all?
Yes, sir. Yes, sir.
Yes, sir.
But still I am not able to write it here. Just a minute. It's taking time. Okay, it's now opening. So we were at so is it visible now? This is the same tutorial sheet which we have looked at earlier. I will just scroll little bit up and try to derive it again here. Just a minute. So whiteboard is now clearly visible to everyone,
Yes.
Yes, sir.
including the writing, whatever is there.
Yes, sir.
Okay, so the equation we have obtained was this. From the balance equation, what we have obtained is this. Tm is given as minus r square by 4 km minus r square by 4 km psi v plus C2. This is what the equation which we have obtained. And now the new boundary condition for the given problem is, the new boundary condition for the given problem is at r equals to r naught, at r equals to r naught. What we are going to get is Tm will be equals to Tw, isn't it? And Tw we have already calculated as 215 degrees Celsius, correct? So we apply this boundary condition, what we get is Tw r naught square by 4 km psi v plus C2. From this what we are going to get is C2 is obtained as Tw plus r naught square by 4 km psi v, isn't it? Now we can put it in this equation number 1. This is equation number 1. This is 2. Put C2 in 1 So by putting C2 in 1, what we are going to get is Tm. Tw will remain as it is, plus psi v by 4 km r naught square minus r square. This is what you are going to get, isn't it? For maximum temperature at center, R will be 0. So what you are going to get, Tm will be given as Tw plus R naught square by 4 km psi v. So this is what the equation which we have used for calculating the center temperature, isn't it? This is the same equation I have used for calculating the remember, this is the same equation which I have used here in the presentation. So if I go back here in the problem statement, the equation which we have used, is my slides visible?
Yes, sir. Yes, sir. Yes, sir.
Yes, sir.
So this is the same equation I have used here. Remember, see, Tm is given as psi v r square 4k by Tw, and this is what we have calculated at the center. So this r is r naught here. Okay. And with this, we calculate the center temperature as 231.6 degrees Celsius. Is it clear to everyone what we are doing? Hello?
Yes.
So
Yes,
we
sir.
stop here, and from the next class, we will look at unsteady state. Okay, so far we were looking at steady state. We will start with the unsteady state conduction from the next class. Okay, so we stop here unless you have any doubt, any question to ask.
Sir, I have to just ask one question. Sir, at steady state, we look at the condition when the temperature profile has been developed.
Yes.
Am I right? Am I
Yes,
right?
yes.
When the whole temperature gradient and temperature profile, we can mathematically write it like we have
So
written.
accumulation, okay. So see, accumulation term we are ignoring. So accumulation term is with respect to time, isn't it? So that term we are not including in your shell in our shell balance. That's why we are calling it as a steady state. So temperature is not varying with respect to time. But later on, from the next class onward, you will see that even temperature profile is varying with time when we are looking at unsteady state. Okay.
Okay, sir. Okay, sir. Means at steady state, input is equal to output, and there is no accumulation.
There is no accumulation term. Yes. We have taken generation term, but we have not taken the accumulation term. Okay. So is there any more question from anyone? So if there is no question, let us stop here, and we will have a tutorial on Wednesday 1 to 2.